Well, don't know the strong
is on.
Don't know yet. Not yet. Anyway, okay. So today I'm going to be talking about basically my research, which I threatened to talk about a long time ago, and the day has finally come. So today is the day of reckoning. It's finally happening. Yeah, it's Armageddon, which means it's going to be a hardcore compiler talk. So apologies in advance for, and please stop me if you have questions about a specific compiler thing I say, because I'm almost certainly just going to blow through some detail that is actually important if you don't already know it. So please stop me when that inevitably happens. But anyway, today I'm going to be talking about programming heterogeneous systems. So talk outline. So first I'm going to talk about what the hell I just said, what is a heterogeneous system, why do they matter? Then I'm going to be talking about Hercules, which is a kind of research compiler I built to do the aforementioned thing of programming heterogeneous systems. And then I'm going to be complaining. That's the third part. Okay, so if any of you have been in a research talk in the last 10 years related to computing performance or hardware or compilers or programming languages, you've probably seen a chart that looks like this, which basically says that compute performance is no longer coming for free. You can't just rely on Moore's law to make your computer 2 times as fast the next year or whatever. We actually have to get a little bit more clever. The primary way people have been getting more clever is through hardware specialization, which is basically instead of putting more transistors into your CPU to make a bigger CPU or a CPU with more cores or whatnot, and that certainly happens to a certain extent, but a much larger trend is to specialize those transistors. So kind of the most mild example of this is the GPU, where if you look at the transistor budget put into making a CPU versus a GPU, to massively oversimplify things, GPU, much more of the transistors are spent on actual logic and compute than in the CPU case. And in practice, because of how the GPU is architected, you can use a lot more of that compute at the same time than the CPU. So you get much higher overall compute throughout. Yes?
So what do CPUs use the resistance for?
Cache. When Intel sells you a CPU, 90% of the die area, a very large percentage of the die area is literally cache. So they sell you a bunch of SRAM, basically.
There's no cache in GPUs?
There is, but it's far less. It's, these numbers are not correct, but think of the CPU as being 90% cache and the GPU being 10%. And by cache, I mean SRAM.
The other thing is that, in the CPU, when you actually go to RAM, it's really far away because it's just a separate discrete component, whereas the GPU, it is a discrete die, but it's right next to each other, usually runs at an order of magnitude faster than typical CPU RAM, and is put physically near as possible giant memory.
So the phenomenon that Jenna is referring to is something called integration, which is another way to make computers go faster. Integration is putting things closer together. So it is typically the case if you look at a gaming PC, for example, that your CPU memory is less integrated than your GPU memory. That's not necessarily inherent to CPUs versus GPUs. That's more just how the current industry players happen to structure things. But anyway, okay. The problem is that we still want our computers to do a bunch of things. So maybe a more extreme example of a specialization is something like a TPU, like a tensor processing unit, which basically just does deep learning, right? And that's much more specialized than a CPU. But often you still want your computer to do a bunch of kind of general things. So even if you have a computer with a bunch of TPUs, do a bunch of ML on it, it still needs to connect to the network so that it can communicate with the outside world, because otherwise, why are you doing this in the first place? So for that, usually you need either a CPU or a network interface card, or the combination thereof, in order to actually communicate with the outside world, which means if you want your computers to actually do general things, you need to put a bunch of these different specialized chips kind of in the same box. So you need to have one computer with multiple different specialized chips. So it's not just a box full of TPUs, it's a box with a TPU, a GPU, and a CPU. And sure enough, this is what Apple's new SoCs look like. So this is a kind of a very pretty block diagram that shows that a modern Apple chip has a CPU, a GPU, and what they call neural engine, basically TPU, kind of in the same package. And this is what I'm referring to when I say heterogeneous system, is you have multiple different ways of doing compute in the same kind of unit that gets sold. Okay. I think simplest example that's been around for the longest period of time of a heterogeneous system is actually gaming PCs. Now, in the modern incarnation, this is basically, an x86 CPU plus NVIDIA GPU. This is like the most common version of a gaming PC. And if you look at like how this works, like, okay, how does a modern game actually run? Is that you basically have a lot of your kind of logic, your, the AI logic of like the entities in your game, you have the physics logic, all that gets processed on the CPU. And then you send a bunch of information about your scene to the GPU, which then renders it into a frame that then gets displayed on your monitor. In this case, what's being displayed is Super Tux Kart, because of course that's the only video game you can play. Nowadays, games that are worse than Super Tux Kart and more computationally demanding, they will often do other stuff in the GPU as well, such as graphics. But this is kind of the basic idea: is that your application, the application being the game, a lot of the processing is going to be on the CPU. Some of it's going to be on the GPU, and there's like an explicit, we're going to decide ahead of time, like this part's on the CPU, and then the graphics part is on the GPU. Okay. So the question is like, how do you actually program this? Like, I want to use the GPU to, render in my game. Like, how do I program it? Like, how do I write the game? Okay. So there's a bunch of different ways you can program a GPU, and they all have their trade-offs and oddities and other things I will not say right now. But all of them pretty much have kind of the same fundamental model, which is that you're actually not going to write one program, you're going to write two. You're going to write one that runs in the CPU, and you're going to write one that runs in the GPU. And what the CPU program does is it basically tells the GPU what to do. Is it basically controls it in some way. It says, okay, here's some data, do this thing on it, and then give me the data back. The GPU code is what actually does the processing. So it's what actually renders things or computes, what color each pixel is going to be. So, okay, you write two programs. And like I said, the CPU is responsible for controlling the GPU. This system often has, or this programming model, and we'll get back to that, has this thing called distributed memory, where the CPU and the GPU have different address spaces. So when you want them to communicate, you have to be very explicit. So you literally will have to call a command that's like, copy this data from the CPU to the GPU, or vice versa. You often have to explicitly synchronize between the two devices. And then often these APIs are also asynchronous, because you might want to launch multiple tasks to be run on the GPU at once. The point here is that all of this is a bunch of complexity. So the point here, beyond the kind of specifics of what it takes, is that programming heterogeneous systems is very tricky currently. And let's look a little bit closer at this example. So what this example code is doing is it's basically just taking two vectors, and it's kind of doing an element-wise multiplication of each. Okay, so if you look closely, so this is written in C with CUDA extensions. Now, if we look at this closely, we kind of see that there's some annoying points of this, at least compared to just the C code. So first of all, I refer to this as there's an explicit partitioning of code. Basically, what this is saying is that you have to write two programs. So this function here that's marked as global is one program, that's part of the GPU. And this part down here, which actually calls that function, is another program, and that's on the CPU. So you have to, at the time you're writing the code, you have to upfront decide what's going to run the CPU, what's going to run the GPU. Okay. Second, like I said earlier, these two devices are they're modeled as having different memory spaces. So you have to explicitly copy memory from the CPU to the GPU, and then do the GPU processing, and then back from the GPU back to the CPU, presumably if you want your CPU to do more things.
Is this model still true for like the new Apple integrated?
We'll get to that. Short answer is yes, asterisks. Surprisingly. Yes.
Are there things that GPU cannot do?
Are there things GPU cannot do? Yes. In what sense?
So I mean, what if I just run all the code on the GPUs, then I just don't use the CPU at all?
Well, your GPU doesn't talk directly to the operating system, so the program is going to not do anything visible. The GPU can't do I/O effectively, so you can't read or write anything to files, you can't do anything on the network. And yeah, so it basically can't do any I/O.
So where I need to do actual computation, I can copy data to the GPU, I can run a calculator, and without that, I cannot just run the entire program. So limitations to non-computing tasks.
Yes, that's one way to think about it. Yes, that is true. It is also true that for a lot of things, the GPU is actually slower than the CPU to execute a particularly compute task. So there are things other than I/O that you still might want to run on the CPU. Okay, so this explicit copying to and from the device is, I mean, it's more than just annoying, because imagine, let's say, okay, I have this, vector multiply here. Let's say I put another vector multiply below, or something else, some other GPU code. Well, then all of a sudden, it doesn't make sense to copy the data back to the CPU, because I still want it on the GPU. So now, whenever I make a change to my code, let's say I add more computation to the GPU, it kind of affects code I previously wrote, because I'm writing all this kind of manual data movement between the CPU and the GPU. And you have to write that data movement kind of in the headspace where you're thinking about all of the compute you're doing. So this is really annoying. And there's also a bunch of like weird device specificities. So this thing here, this like angle bracket notation, basically it says like how many blocks and threads you want to spawn, which is kind of a GPU specific abstraction that doesn't really make sense on the CPU, so this is kind of annoying. And then when you write the GPU program, use this block IDX and thread IDX thing that don't correspond to anything on the CPU as well. So this is like a GPU specific phenomenon, which further underscores that these are really two different programs and two different languages. Yes?
I've been told that GPUs can't do conditionals and branch statements. I was never told the reason why.
So they can do conditionals and branch statements. It's just, it will, depending on how you do it, it might be slower. Okay. And that's down to, that comes down to kind of specific architectural details of GPU.
So it's still something which is faster than CPU.
Potentially. It depends on what kind of branching you're doing.
Okay.
I'd be happy to go into more detail on that after, but
okay.
Yeah. And then also there's another thing which I didn't show here, which is like you have to often explicitly synchronize between the CPU and the GPU. In this case, you don't, because CUDA by default actually like tries to do synchronization for you, which is often pessimizing. So it'll actually, CUDA behind the scenes, unless it is on the optimization, will actually do a synchronization between each one of these columns just to make sure it's correct.
What does that actually mean in this case? If there's like a lock, that it blocks until it's done?
Yeah, basically, you can't call this CUDA memcopy until this one's finished. Okay? And you actually look, like these two memcopies, if these don't overlap, you can do them at the same time. So that's potentially suboptimal. And if you want to get the best performance, which like the whole reason you have a heterogeneous system is you want to get better performance, right? Otherwise, you just put everything in the CPU. So if you're writing heterogeneous code, you want to get the best performance. In that case, you don't want to be paying stupid overhead for implicit synchronization. Right? So in real world CUDA code, you manually synchronize, which is a pain. Okay, so just to kind of enumerate the challenges here. One other thing I didn't mention yet is that these APIs, so like CUDA, OpenGL, Vulkan, they're all really error prone and they're really easy to misuse. They don't have very defined semantics in a lot of cases. There's not a lot of type safety. Basically, think like you're programming in the 80s, but it's 2025. That's kind of the vibe you should get. And if you don't want to program like you're in the 80s, this might be kind of annoying to you, and I would agree.
Why is like CUDA still so bad? Or is it inherent to the problem it's trying to solve? Like,
so in the specific case of CUDA,
I guess that would be the one that, at least to me, with a $1 trillion company behind it,
yeah.
I would think like what engineering hours it's not suck.
So I will give CUDA, it mostly doesn't suck, at least compared to the other ways of, OpenGL and Vulkan are even worse. That being said, CUDA is based on C and C++, and it inherits a lot of the kind of fundamental issues in complexity and safety from C and C++. So a lot of the same reasons C and C++ are unsafe are the reasons CUDA is unsafe, except it's even worse because now you have like different address spaces, one for the CPU, one for the GPU. You have like two languages without even making it like super clear to the programmer. Like for example, what does it mean to okay, for example, CUDA C++ is a thing. What does it mean to like C++ in one of the recent standards got like coroutines? What does it mean to run a coroutine on the GPU? It's not very well defined because it turns out if you try to do that, everything will blow up. So like that's kind of an example of what I mean. It's not a fully kind of cohesive system. Okay, another issue is like I said, the CPU and the GPU languages are different. So even in CUDA, if they're in the same file, like you're still writing basically a different language for the GPU code versus the host CPU code. Yes.
I was just going to say about the
sounds like it has in some ways a similar problem to what C++ has, but more so, where they're taking existing things of varying quality and then just trying to bolt more shit onto the side.
Yeah, I concur. Okay, and then another challenge is you have to manually manage memory. I mean, listen, we're a bunch of OS people nominally, so like this shouldn't be too scary to us, but in practice it does kind of suck, especially when you're in a distributed context. And here's the other thing: is like really a lot of this should be like done for you in the sense that like you could figure this out at compile time, and it's not going to have a large overhead because like kind of newsflash, a lot of this memory management could be subsumed by like a stack. Like none of us bat an eye at like stack memory management. Like that's an automatic way of managing memory, but it turns out it's like zero overhead and it just works fine, right? It turns out a lot of memory management you do in a heterogeneous context could be perfectly managed by a stack. We just don't because of language limitations. So it's not just that we must manually manage memory. It's that we must manually manage memory in a really low level way that like, frankly, we've evolved past, at least in just CPU programming, at least in my opinion. Another problem is like I said earlier, is like you have to kind of explicitly decide where your code goes. Like, does it go in the CPU part or the GPU part? And this makes it kind of really difficult to incrementally develop a heterogeneous application. Like, let's say I start by writing everything in CPU code and I want to gradually transition stuff into being on the GPU. Well, now every time I change what's on the GPU, I also have to write all the synchronization and communication and launch code and all that to make all that work. And it's a huge pain. So incrementally developing a heterogeneous application is really tricky. And one other anecdote I just want to point out is that one of these APIs, which is particularly low level, called Vulkan, it is so annoying to program that it's literally not been adopted. Like I cannot underscore this point enough. Vulkan, it was like 10 years ago, maybe a little less than 10 years ago, it was like going to be the new graphics API that everyone's going to use. Like lots of hype around it, right? And it was so annoying and just horrible to use in practice because it was there's too many of these kind of low-level details that are exposed that people did not use it, and everyone's just using DirectX now. So like these challenges do have kind of real-world ramifications, and it does make it harder to program these kinds of systems.
So I've taken a 400 level GPU programming class in the EC department, but I guess we probably never got to the higher level function APIs that you're describing here, because like we implemented matrix multiplication and just very simple stuff.
We're using CUDA?
Yeah.
Okay.
So those are like very low level.
Vulkan's even lower level than CUDA. But CUDA is still pretty low level, yeah.
CUDA is NVIDIA specific, right?
Yes.
So
Vulkan is agnostic, yeah.
Like, do you have an example of that I could understand how Vulkan would be worse than CUDA and for just like implementing matrix multiplication?
And are those at the same level of abstraction? Okay, because you mentioned DirectX.
Yeah, so Vulkan is more tuned for kind of graphics use cases. I would say like one way in which Vulkan is kind of more in the pain in the ass, for example, is like dealing with compute pipelines. So if you want to write a matrix multiply, for example, in Vulkan, so in CUDA, you basically write a function. Like, sure, I complained about this a bunch, but it's not the worst thing in the world, right? You write a global function that's like your matmul, and you call it. Like that's basically what you do. In Vulkan, you have to create this object called a compute pipeline, which represents your matmul. You then have to describe what are called descriptor sets, which describe at runtime the arguments that a function takes and the output it generates. Then you have to allocate buffers on device for the thing, copy the stuff over there, bind it to this thing called a descriptor, which allows you to put it in the pipeline and get something out. It's just a lot more hassle, effectively. So that'd be one example. Synchronization is also a massive pain. In CUDA, it's like one line. In Vulkan, it's like 20. Okay, so these are all the challenges with programming these heterogeneous machines in practice. Next, I'm going to talk about some ways of fixing them. So one way of fixing them is to use effectively domain-specific languages. And I'm really talking about deep learning. Like we all know what we're, who am I fooling here by not saying that? So in these approaches, so you have something like PyTorch or JAX or TensorFlow. If any of you have used any of these, then basically you know that the kind of principle is that you write kind of these high-level expressions in terms of how you want to do math on tensors. And the underlying framework will kind of automatically figure out how to map it onto onto GPUs, for example. And this is some pros. So it's very transparent to the it's very easy for the programmer to use. So like they just have to write their tensor expression. In the case of JAX, like it's literally just a tensor expression. And the compiler will automatically figure out how to map it on the GPU. And it usually does a pretty good job. I should add that the reason it does a pretty good job is that there's been so much research and also just like industry development that's gone into making these compilers work well in practice. So although like it is a very pretty user interface, there's a lot of work under the hood to make these things work. And the cons are that one, it's domain specific. So it only works if you have like tensor expression. And one of the problems there is that there's very limited control flow. So like if you want to do arbitrary control flow and express that inside of your GPU program in like JAX, for example, I mean, it might be possible, but it might not be. And even if it is possible, it's kind of a pain in the ass. And there's no guarantee that it's actually going to get like compiled to fast code. These also don't play nice with code, what I'm going to call like outside DSL. So if I have code that's like other GPU code, let's say I have graphics code, right? I also want to run the GPU. And let's say I want my GPU graphics code to talk nicely with my GPU deep learning code. Getting those to like play nice with each other, getting one to talk to the other, if the deep learning code is in PyTorch, is really hard. And in practice, it's not really something you can do unless you want to go through a whole lot of pain. And also, fundamentally, it's still two languages. Like you still have Python that's on the CPU kind of controlling things, and then you have like these kind of tensor, programs that are executing on the GPU. And here's kind of an example code snippet of PyTorch. And it's very nice that you can just kind of like write a very simple tensor expression and get some good results out of it. But it's still kind of annoying to use in practice for some of the reasons I mentioned. Okay, so that is, I think, yeah. So those are kind of the pre-existing challenges that exist when it comes to programming these heterogeneous machines. And DSLs are one solution. I wanted to design a solution that allow you to program these machines without being domain specific. And fundamentally, one of my kind of one thesis I wanted to explore was like that a lot of the techniques that these domain specific compilers use, you can actually use in a general purpose context. Like there's nothing kind of inherent to tensor programs about some of these techniques. So I developed two things. So one is Juno. Juno is a programming language for programming both CPUs and GPUs simultaneously. And then a compiler called Hercules, which actually compiles these into CPU code and GPU code that you can then actually run. So at a very high level, what the whole system looks like is you write Juno code. Juno code consists of two things. One is the application. This is what you normally think of as a program. It describes like literally what the program does. There's a second component called the schedule, which we'll get to. It basically tells the compiler how you want to compile this program onto a machine. Because potentially, you can take a program and compile it in many different ways. You can take this part, put it on the GPU, this part put on the CPU, or you can put this part on the CPU and this part on the GPU, or both on the GPU or both on the CPU, or you can put them all as like one unit on the CPU. And you need to tell the compiler what way you want to do this. And we chose to have a separate language or a separate part of the program called the schedule that effectively tells the compiler, how do I actually want to map my application onto a machine? Then we have an intermediate representation, which is basically a data structure that represents your program. We do a bunch of optimizations on that, and then we lower them through a couple backends, either to CPU code in the case of the LLVM backend, or to GPUs in the case of the CUDA backend. So first, like, what does Juno look like? So one thing I really want to emphasize is like Juno is not that weird. So this here is like an example of a matrix multiplication function. If you stare at it, it kind of just looks like a matrix multiplier that you would see in like C or Rust. Like it's not rocket science. Like it's really not doing anything that weird. I want to make sure I emphasize that. So like if we look, if you've seen the kind of classic triple nested for loop formulation of matrix multiply, this should look familiar. We take in two arrays, we allocate a new array, we kind of do this triple loop accumulation into that array, and then return. So it's pretty bog standard. So that's the application code. On the bottom, we have what I call the schedule code. And I'm not going to go into super deep detail about what each individual line does. But basically what this is doing is it's telling the compiler, how do I want to map my application code onto a machine? And this is important because there are many different ways you can map an application onto a machine, and that'll have drastically different performance consequences. And One thing that compiler researchers have been chasing for a very long time, the kind of holy grail of compilers research, is having the compiler effectively automatically figure out how do I want to map an application onto a device. And it turns out this is really hard in practice. Compilers are pretty good at doing this in the case of CPUs, but less good in the case of heterogeneous machines. So the approach we took was to basically say we're not going to tackle that problem, at least for now. For now, we still require programmer direction to kind of tell us how we want to target the machine. However, I should note, the schedule here is it's a separate thing than the application logic. So you can, for example, write the application logic once, and then let's say I have two machine configurations, one with the CPU and one with the GPU, right? Or one with the CPU and one with the CPU and a GPU. I can have two different schedules that basically tell the compiler to map the same application to two different machine configurations, one that only has a CPU and one that also has a GPU. So in the paper, we call this being able to productively program heterogeneous machines. We make the argument it's much easier to write a schedule if you know what you're doing than it is to rewrite your application for every new kind of machine that you end up targeting. That's kind of the fundamental argument. Okay, so this is kind of a very brief diagram that kind of like visualizes what that schedule does. Again, the specifics here don't matter too much. All that matters is that we can take this matmul here, which is not at all optimized. Like this is written in the most like bog standard, like straightforward, sequential, non-parallel. Like there's nothing fancy about it. And just through our schedule, we can convert it into an optimized matrix multiply that gets high performance. So that's the kind of main point of this diagram. And this basically just shows the kind of blocking loop structure. Okay, so that's the language. How do we actually optimize these programs? So the Hercules compiler has an intermediate representation called Hercules IR that we use to actually optimize these programs. I'm going to very briefly describe Hercules IR because one, we don't have too much time, and two, this is not a talk about compiler optimization. But basically, the gist of it is that Hercules will represent the entire program as a graph. So each function is a graph, and then functions can call other functions. What the graph describes is it describes the dependencies between different kind of operations in your program. So for example, if I have a program that takes two numbers and adds them, you'll have a node that represents I want to add two numbers, and I'll have two incoming edges from the things it's adding. And then if it has anything and then if later in the program you use the result of that addition, like you return it, for example, there will be an outgoing arrow from that.
So that graph has no sense of like the sequence of things or the procedure, right? It's just like a dependence relationship.
Correct. I mean, there is some sequencing because if I have an operation that depends on another operation that depends on another operation, there is a sequencing there implied by the data dependence.
Right.
But if I have two nodes that there's no edges between them, then there's not implied data dependence. So we represent both data dependencies and then also control dependencies because those programs have control flow. So this particular control flow represents this loop here. Again, I'm not going to go into super high detail, but you can look between nodes 16, 8, and 3. Note that there's a cycle. So edge from there to here, from here to here, and then here to there. And what that cycle represents is the loop, right? It's basically, I do one iteration of this loop. Okay, I'm not done. I'm going to go back up. We can, just to kind of visualize it again, this is what the matrix multiply program I showed earlier looks like once you convert it into our intermediate representation. And part of, I'll very briefly point it out, and if folks have questions, I can answer later, but one other part of our program representation that is quite important for optimizing things in practice is that we have a kind of an explicit representation of parallel loops called fork joins. And this allows us to do a lot of loop optimizations much more easily than other compilers. And also, if you want to generate GPU code is parallel. So you need to be able to know when you have a parallel loop. And that's what fork joins allow us to do. More details on how we figure those out in the paper. But, so a couple things to note. So first of all, there's a single language, which is Juno, for writing code on both the CPU and the GPU. And if you want to write GPU code, it's not a different language than the CPU. It's not like CUDA, where even if it's in the same file, you're kind of writing two different languages. It's still just one language. So that matmul there can, based on the schedule, can either become high-performance GPU code or high-performance CPU code. There's no difference in the application code. And then second, one other feature is that the communication is implicit in the function type signature. Okay, that's a lot of words, but I mean, what does that mean? I don't have to explicitly copy data to the GPU and back when I write this code. So let's say I'm putting this in the GPU and then I want to call it. Well, how does Hercules know, okay, what do I need to put in the GPU and then what do I need to take back in the CPU? Well, if I'm calling this code from CPU code, let's say, I have some code on the CPU that's producing the inputs and then some code on the CPU that's going to read the output. Well, okay, let's look at this function. So it takes in two arrays, takes in an A and a B, right? Part of the type of the arrays is the size of the array, these kind of N, M, L. So I know how much data I need to copy over. And then also I know I'm returning this array that size N by L. So just by looking at the type signature, I can tell what data I have to copy over to GPU and what data do I have to copy back when I call this from a CPU function. Okay, how do we actually generate code? So once we've optimized the Hercules IR, what you can do is that basically every function you can lower to a single device. So we have a couple of different backends. So the LLVM backend is what generates CPU code. The CUDA backend is what generates GPU code. So if you want to generate a CUDA function, you send a Hercules function to the CUDA backend, and it'll spit out CUDA code that basically implements that Hercules function. Same thing to LLVM. And then any functions that you mark as entry, which is basically saying, I want this to be a function that I can actually call from outside my Hercules application, we generate like basically a Rust interface for that function. And the use of Rust here is not super important. It's basically just a stub so we can call our Hercules code to make that work in practice. There's no reason you couldn't just have a main function in your Hercules program and then like link that against libc's kind of start routine. There's no reason you couldn't do that. We just hook it into Rust because it's easier to benchmark that way and easier to do I/O and some other things. Okay, so some key takeaways before I start complaining. So one is that using our language, you can write your application logic in a single target agnostic language. So you don't have to write code in two different languages if you want to program the CPU and the GPU. And also in this work, I should note that we did target specifically CPUs and GPUs, but there's nothing preventing you from targeting other devices such as like FPGAs. And then by using schedules, you can compile a single application to multiple different machine configurations without modifying the application at all, which makes it a lot easier to incrementally develop heterogeneous applications. And then one thing I didn't talk about here is that we get like really competitive performance with previous systems. Again, more details in the paper, but this doesn't come at the expense of performance, is basically the point. Okay, time for new complaint. So, so the kind of assumption we've been making so far about what a computer looks like is that, okay, we have some like CPU and its associated memory, and we have some GPU and its associated memory, and they talk over PCIe, and the CPU kind of controls the GPU through talking over PCIe. And this is like well and good, but this is not actually how like a modern computer looks. A modern computer looks a little bit more like this, where you have actually multiple CPUs because you have multi-core CPU. They share a single memory address space, so that's a single coherent shared address space. And then it talks over PCIe, not just to a GPU and its own memory, but also a bunch of other devices. In a heterogeneous compute case, I'm listing like FPGA, TPUs, and those kinds of things because those are other devices people are interested in programming. But in like your phone, this might be something as kind of simple as like a security coprocessor, like that does like AES encryption, for example, or kind of attestation, or those kinds of things. So these might not be kind of your big ticket items, for example. The point is that your modern system is actually a lot more complicated. It's actually, in some senses, it's a complicated distributed system, even though it's nominally a single chip. And these are really difficult to program. And in particular, there's kind of an unfortunate nature here, which is that you'll notice that the CPU, the GPU, the FPGA, the GPU, they all have different memories. And if you'll remember, originally at the start of the talk, the reason I said that we care about heterogeneous systems is that we need to do hardware specialization to get better performance, right? That doesn't have anything to do with memory, right? Like at the end of the day, like these memories are all the same SRAM. Like there's nothing physically different about them, usually. So ultimately, what this kind of architecture does is it conflates the kind of difference in compute architecture, and it also with making the memory hierarchy more complex. So by having all these kind of distributed memory address spaces, you're making memory hierarchy more complex. It is harder to program this kind of system than if all of these devices could communicate in the same address space. And I hope I've done enough to convince you that programming different compute architectures simultaneously is already hard enough. We don't want to make it harder. So I think this is a rather unfortunate feature of many modern heterogeneous systems. Luckily, I'm not the only person who thinks that, because if you remember back earlier when I was talking about this Apple chip, you might notice that we have the CPU, the GPU, and the neural engine, but they all talk to the same view. So at least Apple, they designed their SoC such that all of their different compute architectures actually talk to each other in the same kind of unified address space. And this has this has benefit of being a single coherent address space. So this should be way easier to program, right? Like okay, great, Apple's listening to me. I'm so right. And we all know, Apple has dominated the personal computing market forever, and we all love the bounties of programming Apple devices, right? That's obviously what happened.
Your $10 donation from them, like they give to the BSC Foundation.
I was not aware of that. Well, anyway, so okay, point is that it's not true. Obviously, it turns out it's not actually easier to program this than that, because guess what? And I actually looked at this because I was surprised. I looked, so if you want to program, in particular in Apple, it's Metal is their framework for programming the GPU. You still have to manually memcopy things. If you want to, you still have to manually say, I have this GPU buffer and I have this CPU buffer, and I'm going to do a memcopy, and I have this explicit synchronization, all this. It's not actually any easier in their programming system, even though the architecture should make it way simpler.
Is that because the fabric hard codes separate address spaces on the RAM for each thing? Or
No, as far as I can tell, the reason is because that's how the other graphics APIs do it. Which,
But don't you have memory addresses that in the GPU that you can write to, and wouldn't 0 for the GPU's memory space map to the same thing as I don't understand how.
well, the point is that
where does this divide actually happen?
it's all in software, because you can always implement a distributed memory software system on top of shared memory hardware, right? You just artificially chunk things up, and that's what macOS effectively does. Yeah.
So, this I think might be basically what you just said, but my first thought when you said that was it doesn't have something to do with virtual memory. Virtual memory is mostly a CPU abstraction. It's not really a thing in the GPU as far as I'm aware.
Yep.
So they want that abstraction layer so that they can
Keep the CPU stuff the way it is.
keep the CPU conception of virtual memory the same, because everyone has gotten used to and usually reasonably happy about
The point is
virtual memory works.
that defect is entirely a software defect.
Oh.
You could write an operating system that does this properly. They just didn't.
Yes, I wasn't saying that it's not.
Yeah.
So you mentioned that GPU is no more intelligent without a CPU, which I could definitely agree to that. But I assume that most modern architectures and operating systems, most memory transactions are all handled by DMA.
Mhm.
So on the Apple example on the right, I'm assuming the fabric is what's creating each device and amount of DRAM. Is that accurate? Because obviously the CPU still has to tell the GPU to perform the direct memory access, but there's very little weight.
That's not necessarily true. The GPU can issue DMAs on its own through load and store instructions, just like the CPU can.
Okay.
If you have a separate GPU card with its own memory address space and DMAs, it's certainly not waiting on the CPU to tell it what DMAs to do, right?
Yeah.
So what I think, and this is me complaining, so this is gonna be about what I think, is that fundamentally this is a software problem, at least in part. And I'm not, thankfully, so that I can at least feel a little secure in that, I'm not the first person to think about this. So I'm actually gonna end my talk by telling you should go watch this talk, which is it was the OSDI and Usenix 2021 keynote by this chap named Timothy Roscoe. He's a professor in Switzerland. Very good talk. It basically, the title is It's Time for Operating Systems to Rediscover Hardware. Basically, the point of the talk is that modern Linux does not really understand modern hardware. So what he's done in this particular picture is he's circled all the different cores on this kind of larger SoC that have their own address space. And Linux runs on that core. So like, see that little red circle? That's where Linux runs. The rest of all this, there's a bunch of other kind of shadow operating systems and real-time kernels and all sorts of other crap that manages the rest of the system. And of course, when your operating system use like 10% of your chip, you're not going to have good software abstractions around how to program the other parts of your chip, because ultimately you need the operating system to provide the programming abstraction, because the operating system is what abstracts hardware. That's what the operating system does. And modern day Linux doesn't know about most of the hardware. And that's how you get into the scenario we are now, where you have, kind of these distributed memory architectures where you're sending kind of messages in a bottle to all these other chips and hoping you get a response back. So I think we should really be moving, at least architecturally, to something more like this, where you have in a single SoC, you have all of your compute architectures under the hood be in the same single coherent address space. But more importantly, the operating system has to know that, has to build a virtual memory abstraction on top of all of that, a single virtual memory abstraction for all of the compute architectures, so that they can actually communicate through shared memory, which would make programming a lot easier, both in terms of communication, but also in terms of synchronization. Because it turns out it's also way easier to do synchronization in shared memory than it is in a distributed system as well. And with that, I yield my time. Any questions?
What is Parker architecture referring to?
Oh, just a particular SoC architecture. I think he has like 5 slides with 5 different SoC architectures, so it's entirely non-specific.
So I strongly see your point about like we just need a better way to do virtual memory. Since we have with the heterogeneous system comes a more heterogeneous conception of memory. Do you have any ideas for how we should? Because I'm trying to think like how can we take page memory and make it work in the way that page virtual memory, the way Linux does it, doesn't generalize to like across the CPU and GPU very gracefully, at least in my head.
Yeah, so the way to think about this in my view is that each compute architecture internally has its own weird memory hierarchy. Like the CPU has L1 through L3 caches already. That's its own weird memory hierarchy. The GPU has global shared constant local memories. That's its own little weird memory hierarchy, right? I think the top level memory hierarchy should be a shared single address space coherent address space. So that would be global memory on the GPU, and that'd be DRAM on the what you currently think about as DRAM on the CPU. I think that should be coherent. The levels of the memory hierarchy that are lower than that, on the CPU, those are all hardware managed. On the GPU, those are software managed. Those, I think, those should be separate, obviously, because those, if you don't have them as separate, you can't fix performance. So I think you want a single address space that's coherent, that everything talks through. But then there's plenty of room below that where you can put memories, where you can actually get good integration, where you put memories closer to your specialized chips in order to get good performance.
Sure.
Because we understand well how to generate code for these devices that takes advantage of those lower levels of memory hierarchy. What we don't have a good understanding right now is how to develop a programming system that allows all of these devices to communicate at that top level memory hierarchy, of the memory hierarchy, which is what I would want as the single coherent address
Yeah,
space.
but I guess my concern is like if we have this like unified address space, how since virtual memory is like a CPU abstraction, it doesn't exist in like the rest of the system. So like, how do we build virtual memory across the entire system, just so that I can't say write a program with the GPU component that just loads these values and then tells me what they're them as a way to circumvent virtual memory?
So GPUs do have some they do have a concept of virtual memory. I don't think it's obviously not exactly the same, because it's not like in Linux, for example, right? It's like just like on the single GPU because it has its own address space. But I actually don't necessarily see why you couldn't do a kind of virtual addressing scheme locally on device. It's just basically this top level coherent address space is mostly for communication and kind of intermediate data storage. But I don't see why you couldn't basically just have every single device, not just the CPU, talk to it through a page table effectively, right? You just, in the case of like the GPU, you obviously don't you can't go through that too often, right? Because it's, very high performance overhead. That's why you have your lower levels of memory.
Yeah, and I guess what I'm trying to reason through is like, how do we design something where you get that address-based integration and like, maybe I'm misunderstanding like the goal, but I see that like you want to have that global integration and keep the like expected security constraints of virtual memory. All the systems need to agree, at least to some extent, to virtualize memory the same way.
Yes,
and
this is true.
Synchronization with like, now every component needs to have a concept of a process, at least to the extent of like, we switch between different virtual memory spaces.
Yes, all the components need to agree on the operating system conventions, at least in terms of the interface to the operating system. They all need to agree on the virtual memory conventions. But like, we're talking about a bunch of different IPs on the same chip. So nominally, it's one organization making the chip. So at least in theory, that is a consensus that we should be able to get.
Yeah, I'm not saying it's insurmountable. I'm trying to like figure out like what are the problems to just doing this, besides, chips are expensive.
Yeah, but you definitely need that consensus. That is for sure. And it's like, like you said, it's not just virtual memory. It's also, in practice, operating systems allow you to do multi-tenant execution. So this also means that the operating system not only does scheduling for the CPU, but now also does scheduling for the GPU and potentially what other devices you have. The GPU already allows multi-tenant execution. It's just that scheduler is in the driver on the GPU itself. It's not baked with the Linux scheduler. I think that a truly heterogeneous operating system, if you would call it that, the scheduler would simultaneously reason about CPU scheduling and GPU scheduling, and what other other device do you have scheduling as well.
Is there interest in high performance computing applications to start using SoCs from Apple? Is it feasible?
Well, there's a lot of, I would say, homebrew enthusiasm about doing deep learning on Mac chips, because often those are the best chips in terms of dollars spent per gigabyte of memory you have. And a lot of these applications are bottlenecked by total memory size. So there's been a lot of, like I said, homebrew enthusiasm about using the Mac chips for deep learning. For, let's say, more serious deployments, I don't know, probably not, because that's just not the market that Apple's typically targeted. But I think that's not a technical limitation. Like, I don't see why you can't take a chip that looks like that, maybe scale it up a bit, and sell 10,000 of them to someone that's going to put them in a big room. That's effectively, NVIDIA is also doing this with their Grace Hopper chips. They just don't talk about it like this, and I think they use Linux on that and do some god-awful Frankenstein thing on it.
Yes, they do.
Yeah, so NVIDIA is doing this as well. Everyone, like, this is the design everyone's kind of going to eventually, because it is what makes the most sense.
NVIDIA is doing updates right now to do a DMA transaction between the network cards and the GPUs with no CPU involvement, and they're doing that at the same time as they're doing Maxwell and Grasshopper or whatever else.
Yeah.
So I don't know if like the industry's diverging into a single architecture, but rather just exploring all the options. Because I don't know if the SoC is specific to desktop use case or if it's actual.
The SoC is used, actually, at least historically, it got its start in mobile. But it's, I think the consensus is that SoCs are the way of the future, and Grace Hopper is an SoC, right? And it is being used in larger scale deployments. Yeah, sure. Yeah. All right. Shall we grab food? All right. Great talk. I'm hungry.